Students, in this video, I'll be talking about a theoretical background of the Ford-Fulkerson algorithm. In the last video, we have discussed what a cut in a flow network is, and we have defined the flow across a cut as summation u belonging to S, v belonging to T, f of u v minus of summation of u belonging to S, summation of v belonging to T, f of vu. And we also defined the capacity of cut S of t, that is C of S of t, is summation of u belonging to S and summation of v belonging to T, C of uv. We'll also go ahead and discuss what is the max flow min cut theorem, which is the basis for the Ford-Fulkerson algorithm. The flow across a cut is defined like this. Let F be a flow in a flow network G with source S and a sink T, and let ST be any cut of G. Then the net flow across the cut ST is F of ST is equal to the total flow across the flow network. We'll try to prove this. We can write the flow conservation condition for any node U belonging to V minus ST, where S and T are source and the sink nodes, as summation of V belonging to capital V, f of uv minus of summation of V belonging to capital V, f of vu is equal to 0. That is, the flow going out of a particular node minus the flow coming into the particular node is equal to 0. Now, taking the definition of the flow which I had just recollected and adding to the left hand side of the above equation, that is, as the value of this particular thing is going to be 0, we just add this. That is, we had this flow across a network as we have defined as summation of f of SV minus summation of V belonging to capital V, f of Vs, and to that you add the above equation which sums up to 0 for all vertices S minus of S. Now this is a mathematical convenience we are using. Expanding the right hand summation and regrouping the terms, we get the below term here. If you notice, it is f of SV minus f of Vs, and this summation of u belonging to S minus of ST, which is equal to nothing but summation V belonging to capital V f of uv minus summation of V belonging to capital V, f of vu, which is nothing but the equation which is shown here as 2611. Now, expanding the right hand summation and regrouping the terms, it can write it as summation of V belonging to capital V, f of SV minus of V belonging to capital V, f of Vs, plus, just expanding this, U belonging to S minus S, V belonging to V, f of uv minus of the same thing here. Now, regrouping these terms, f of V belonging to V, f of SV plus f of U belonging to S minus S, f of uv, the same, then again summation V belonging to capital V, f of Vs plus summation of U belonging to S minus S, f of Vu. Now, if you notice this, these two terms together are nothing but uv, because that is the S is the only term that is missing out in the second summation. So that is together, it can write it as f of uv summation of V belonging to capital V, V belonging to U belonging to S. The same way we can write it on the other side. It becomes summation V belonging to capital V and U belonging to S, f of Vu. Because V is S union T and S intersection T is null, we can split each summation over V into summation over S and T. So by doing this, we can write this equation, that is summation V belonging to S, summation U belonging to S, f of uv, plus summation V belonging to T, summation U belonging to S, f of uv. That is, the first term is split into 2. Similarly, the second term is split into 2. Now once we have split this on this way, we can again regroup. When we regroup, summation v belonging to t and u belonging to s, f of uv minus summation v belonging to t and u belonging to s, f of vu, and the other terms go into this one. Here if you notice the second summation which is within the bracket, they are almost the same term, so they cancel out. This term goes to 0. Now when this term goes to 0, it is nothing but f is equal to summation u belonging to s, v belonging to t, f of uv minus summation u belonging to s, v belonging to t, f of vu. This is nothing but the flow across the cut, and that is what we have proved. Next we'll have a simple corollary to that. The value of any flow f in a flow network G is bounded from above by the capacity of any cut of G. Now this can be easily proven here because the flow value is equal to the flow across the cut, and flow across the cut is given by this equation. Now once we have this is less than f of uv because whatever value flowing in the reverse is removed. And once we remove that, this is definitely less than the capacity, which is nothing but the capacity of the network. So we can say that it is bounded above by the capacity. So f is always bounded above by the capacity of the cut. Now we state this max flow min cut theorem, which is the basis for our Fulkerson algorithm also. If f is a flow in a flow network G with source S and sink T, then the following conditions are equivalent. The first one is f is a maximum flow in G. At the same time, the second says the residual network GF contains no augmenting paths. And the third statement is the flow at that time is equal to capacity of some cut ST. Now these three are equivalent, means they simultaneously hold. In any flow network, these are going to hold simultaneously. F is a maximum flow. In that case, there will be no augmenting paths, and in that case, the flow is equal to the value of the capacity of some cut. Now we'll try to prove this. Proof of max flow min cut theorem. Condition 1 implies condition 2. What does it mean? That is, if F is a maximum flow in G, then there are no augmenting paths in the residual network. For contradiction, let us assume that F be the maximum flow in G and GF has an augmenting path P. Then, by the earlier result which we know, the flow found by augmenting F by Fp, where Fp is the flow in the augmenting path of the residual network, then the resulting flow is strictly greater than the flow F, which contradicts that F is a maximum flow. Hence, condition 1 implies condition 2. Now similarly, we need to prove that condition 2 implies condition 3. What does it mean? Condition 2 is the residual network GF contains no augmenting paths. Implies that the flow at that time is equal to the capacity of some cut Cs of t. How do you prove that? Suppose GF has no augmenting path, that is GF contains no path from S to T. Now we define capital S as set of all vertices small v such that there exists a path from S to V in G, and T is equal to V minus S, that is set of the difference in set of vertices in V and S. The partition S of T is a cut. We have S belongs to capital S trivially and T does not belong to capital S, as there is no path from S to T in GF, that is the residual network. Now consider a pair of vertices U which belongs to S and V which belongs to T. Now if UV belongs to E, that is the flow network, we must have F of UV is equal to capacity of UV, as F is the maximum flow, and otherwise there would have been another edge UV that belongs to EF which would place V in the set S, because we know that V is in T. This is not possible as long as F of UV is equal to capacity. If F of UV is capacity of UV, then this is correct, otherwise it is not true. Similarly, if V of U belongs to the flow network E, we must have f of vu is equal to 0, because otherwise cf of uv is equal to f of vu would be positive, and we would have uv belonging to the flow network, the residual network uf, which then again would place small v in S, which is not true. But if neither uv nor vu is in capital E, then f of uv is equal to f of vu is equal to 0. Hence, we can write that the first thing is true, that is f of st is equal to summation of f of summation of u belong to S and v belong to T, f of uv minus of summation of v belong to T and u belong to S, f of vu, which according to our previous discussion is 0. Hence we can write it as summation of u belong to S and v belong to T, f of v, and according to our first conclusion, that is equal to the capacity of uv, and hence that is equal to the capacity of that cut St. Hence we have shown that the three conditions, the Max-Flow-Mean cut theorem, are equivalent. It also says that when there is a flow in a flow network, it is the maximum flow is equal to the minimum cut capacity. Now we'll try to analyze the Fulkerson algorithm in terms of its time complexity. The running time of the Fulkerson algorithm depends on how an augmenting path P is found. If the augmenting path is chosen poorly, the algorithm may not even terminate. If the breadth-first search is used, the algorithm will run in polynomial time. If the augmenting path is chosen arbitrarily using either BFS or DFS, the time to find a path in a residual network is big O of V plus E dash, where E dash is the number of edges in the residual network. As E dash is greater than E, we can say that it is big O of E, as E dash is less than or equal to 2 times E. So we can write big O of E. The total running time for Fulkerson method is big O of E into F star, where F star is the maximum flow in the flow network. Assuming that every time in the iteration the flow increases, and so we can say that it is F star. When capacities are integral and max flow is small, the running time of algorithm is good. But if the flow is very large and we increase flow by 1 on each iteration, the algorithm will take a lot of time. Consider this example. In this particular flow network, you have S to U has a capacity of 1 million, and U to V has a capacity of 1, and V to T has a capacity of 1 million. Similarly, S to V has 1 million and U to T also has a million. Now we'll try to construct the residual network for the flow shown. The flow is having a flow value of 1 because the path from U to V can take only 1. Now the residual network is given in B. In this residual network, if I find an augmenting path from S to V, V to U, and U to T, which is again having the path value of 1 only, so we go on iterating such that in every iteration the flow value increases by 1. So if you notice this, to reach the maximum flow value, which is around 2 million, it will take a lot of time. We can improve the bound on the Fulkerson by finding the augmenting path P using breadth-first search. We choose the augmenting path as the shortest path from S to T in the residual network, where each edge has a unit distance. Now when I talk about unit distance, it will take only the edge with only 2 edges instead of 3 edges, so that we get first time 1 million path, the next time one more 1 million path, and in 2 iterations only we get to the maximum capacity. This EDMONDS-KARP's algorithm is based on certain properties which we just state without proof. If EDMONDS-KARP algorithm is run on a flow network G is equal to V, E with a source S and a sink T, then the total number of flow augmentations performed would be big O of V into E, and as this is the Fulkerson algorithm runs E times this particular loop, the time complexity would be big O of V into E square. We also have a push relabel algorithm which has a time complexity of big O of V square E, which we will not consider in this course. We'll now discuss one more application of the flow network and the Fulkerson algorithm to find the maximum bipartite matching. Many combinatorial problems can be modeled using flow networks and solved. Maximum bipartite matching problem is one such problem. And what is this matching then? Given an undirected graph G is equal to V, E, a matching is a subset of edges M such that for all the edges V belonging to capital V, at most one edge of capital M is incident on V. We say that the vertex small v belonging to capital V is matched by the matching M if some edge in M is incident on V, otherwise V is unmatched. A maximum matching is a matching of maximum cardinality. In the current problem, we consider the maximum matching in a special graph, namely the bipartite graph. Then what is this bipartite graph? A graph in which a vertex set can be partitioned into V is equal to L union R, where L and R are disjoint and all edges in E go between L and R. We further assume that every vertex in V has at least one edge incident. The problem of bipartite matching has many practical applications, such as assigning human resources to projects and similar other problems. The bipartite matching problem can be solved by converting the bipartite graph to a flow network. Consider this example of a bipartite graph. The graph has 5 vertices in the set L and 4 vertices in the set R, which is given in A here. Now there are 2 edges highlighted which can define a matching. Basically these 2 edges have a matching with one edge incident on one vertex in set L and the other vertex in set R. Similarly, the other edge doing the same thing. There can be multiple such matchings defined. One such matching is defined in B, and this can be the maximal matching, because if you try to add one more edge, then the definition of matching is removed, because if I add an edge from this vertex to this, what happens is it is going to have one of the vertex will have 2 edges incident, which is against the definition of matching. So the maximal matching in this particular graph is 3. We can solve this problem by what we said previously as converting this bipartite graph into a flow network and finding the maximum flow. How do we do that? It is explained in the next slides. It is shown in this diagram. Basically, we add 2 vertices S and T and construct some edges in the left side to form the source and the right side to form the sink. So this becomes a flow network, and if you find the maximal flow in this, it is nothing but the maximal bipartite matching. I'll just explain that. Given a bipartite graph G, we can define a corresponding flow network G dash is equal to V dash comma E dash by adding a source vertex S and a sink T such that V dash is equal to V union S comma T. If the bipartite graph G has capital V such that V is equal to L union R, then the edge set E dash is obtained by adding one edge each from S to all the vertices in L, and similarly adding an edge each from the vertices in R to T, and is defined as E dash is equal to S comma U for all U belong to L union U comma V for all U V belonging to capital E union V comma T for all V belonging to R. Further, we assign unit capacity to each edge in E dash. Finding the maximum flow in the so formed network gives the maximal bipartite matching. This is based on the following theorems, which we again state without proof. Let G is equal to V comma E be a bipartite graph with the vertex partition V is equal to L union R, and that G dash is equal to V dash E dash be its corresponding flow network. If M is a matching in G, then there is an integer valued flow F in G dash with value F is equal to M. Conversely, if F is an integer valued flow in G dash, then there is a matching M in G with cardinality M is equal to F. If the capacity function C takes on only integral values, then the maximum flow F produced by the Fulkerson method has the property that F is an integer. Moreover, for all vertices U and V, the value of F of U, V is an integer. The cardinality of maximum matching M in a bipartite graph G equals the value of maximum flow F in the corresponding flow network G dash. Thank you. You can go through this and study the text also. If you have any questions, you can come back. We'll discuss that. Thank you.